Hi everyone, this is Iman Askari, and thanks for attending my talk on nonlinear model predictive control based on constraint-aware particle filtering and smoothing. In this talk, I would first give motivation for considering the NNPC problem with an overview of NNPC and its challenges. To address these challenges, we take perspective of estimation to solve NNPC and leverage particle filtering and smoothing as a solution. Further, to satisfy constraints in an NNPC problem, we use a barrier function-based method to realize particle filtering and to arrive to our proposed algorithm called the constraint-aware particle filter and smoother, and then use simulation results to validate our proposed algorithm. So nonlinear model predictive control is an optimization-based method that has seen a lot of applications and success due to its ability to predict the future state of the system. So some applications are in the areas of industrial controls and fast charging of battery cells, with application to control formation of drones and autonomous vehicles, with further application in robotics. So let's take a look at the NNPC problem itself. So consider the control of plant using an NNPC controller, where the objective is that the state of the plant follows a reference signal. To fully define the NNPC problem, we have to provide it with an objective function to optimize and a plant model to predict the future states and possible constraints to satisfy. So to solve this NNPC problem, the literature has provided some methods, approaches to do so. And some of them to linearize the plant model, or to use nonlinear programming methods, or use evolutionary algorithms. However, these methods also come with their challenges and disadvantages. So for the linearization case, it introduces inaccuracies of linearization, and we would have non-convexity and local optimality problem for the nonlinear programming method, and evolutionary algorithms could suffer from computational speed. So to address these problems, we take an alternative Bayesian estimation approach to NNPC. And as a sampling-based solution, we use particle filtering and smoothing, since recent studies have shown that sample-based methods could be faster than optimization-based method. And to address the constraint satisfaction problem, we introduce a barrier function method within the framework of particle filtering. So let's take a look at a typical NNPC problem with quadratic cost about minimizing the tracking error of the state and minimizing control effort. And this is such that we consider a deterministic dynamic system and some general inequality constraints. So the optimization procedure would then provide us with a sequence of controls for the horizon H, but typically we would only use the first control on that sequence and then apply that to the plant. So here we ask the question, can we do this differently other than optimization? Specifically, can we estimate the optimal control sequence given the structure of the problem? To show this equivalence, we would consider initially only the structure of the problem and neglect the inequality constraint for now. So then the estimation problem would become about jointly estimating the state and controls given the evidence reference signal. And in order to show this equivalence, we would consider the maximum a posteriori estimation as such. And to go further, we would use the Bayes rule and the Markovian properties of the states to obtain this expression. And given this expression, the second term here is a unity. It would equal to 1 since we consider that the system is deterministic and we assume that we know the initial state x of k. Hence, we would arrive to only this first expression here, where by appropriate Gaussian assumptions, we can see that we can obtain this expression, which relates back to the original NNPC problem of minimizing this cost function here. Hence, we can see the NNPC problem as estimating the joint posterior density given the reference signal with such a state space structure where the reference signal is seen as a measurement with some additive noise, and the control is also a random variable, which these random variables have densities of Gaussian with covariances Q inverse and R inverse, which relate back to the NMPC cost function. So as we saw, the NMPC problem can be realized as an estimation problem of the following. And we note that we only require to obtain the optimal control sequence only at time k. So we can split this estimation problem into a forward filtering and a backward smoothing procedure. And considering the horizon from time k to k plus h, the forward filtering starts from the initial density at time k and goes up to time k plus h to obtain this posterior distribution at time k plus h, and then a backward smoothing procedure to obtain the posterior density at time k, given all of the signal, the reference signal of over the horizon. So to solve this filtering and smoothing procedure, we use the sample-based particle filtering and smoothing. So what is this particle filtering and smoothing about? We use a set of weighted samples, here shown as these bubbles, to empirically approximate the posterior distribution at time t. And then we pass these particles through the Planck's model and weight these particles using the reference signal to obtain the next time steps posterior density. As we continue this up to time k plus h of the horizon, we obtain the conditional density over reference signal. And then we would need to do a reweighting procedure, which in here we do the reweighting particle smoother. We use the reweighting particle smoother to realize this and then arrive back up to time xk, given all of this reference signals. So this summarizes the particle filtering and smoothing procedure. Then we would need to consider the constraints next, as we had neglected it earlier in our formulation. So what is the constraint problem about? So if we have this constraint set where the white dots are the particles that do not violate the constraint set, we are fine. But however, we also do have particles that violate the constraint set. What should we do with these? Should we simply get rid of them? That's probably not a good idea, since if we get rid of particles, we are deteriorating the estimation accuracy of the particle filtering procedure. So instead, we would like to capture the degree of violation and then penalize these particles that are violating to minimize their effect in our estimation. So we penalize their weight. To do this, we propose a modified barrier function, which is continuous. And this barrier function is a parameterized barrier function with parameters alpha and beta, where the parameters alpha and beta are to tune the degree of penalization on the particles. So how do we capture that? Is through using a virtual measurement z with some additive noise, where this virtual measurement z is now incorporated into the particle filtering weighting procedure. And we use this to penalize the particles that violate the constraints. So to summarize the algorithm, we start from the initial distribution and do a forward filtering pass, which is about having the particles pass through the Planck model and then through the barrier function to provide us with the measurement ZT and RT, and then weight that to obtain the next time steps density function. Here, of course, the weights represents the size of the particles. And then we go forward up to time k plus h, and then return back using the reweighting procedure and reweight the particles to obtain the density given all of the signal throughout the horizon of the system up to time k plus h. And then we would extract our estimate of optimal control, for instance, using sample mean. So next, for our simulation, we considered a path following problem of an autonomous vehicle, which this is the starting position of the autonomous vehicle, and we provide a reference path, the blue line here, with boundaries of the track, where now the objective is to track the path as close as possible and not violate any of the constraints in both the acceleration, steering, and the boundaries of the track. So our proposed algorithm was effectively able to do so. And for a benchmark, we still use a particle filtering framework, but without the constraint awareness. And here we can see that there is violation of the constraints in both the steering and the track's boundaries. Further, we also considered recently a motion planning problem, which is about setting a goal position where there is no reference path for the car to get to that position and needs to obtain a feasible path without any collisions with other obstacles. And here for the scenario, we considered a curved road with a dynamic environment where the other obstacles are also moving. And we see that the ego vehicle, which runs the proposed algorithm, is able to provide a safe trajectory without any collisions. And this is while we satisfy the control constraints and maintain a nominal speed for the vehicle. And this, the relative distance between the cars also show that there is no collisions between the obstacles. So in conclusion, to address the challenges of NMPC, we formulated the Npc problem as an estimation problem and considered the constraints using a barrier function method, and then leveraged a filtering and smoothing procedure to obtain the densities and obtain an optimal control sequence, estimate an optimal control sequence. And we showed the efficacy of this proposed algorithm through two types of simulations. And that is it. Thank you. Any questions?